Hello everyone. We solve problems from the chapter of elasticity. This is a simple problem. A steel material has Young's modulus 2 into 10 raised to 11 Newton per meter square. Bulk modulus is also given. We have to find Poisson's ratio and modulus of rigidity of steel. The problem is simple. We only have to use the formula which relates Young's modulus, Poisson's ratio, bulk modulus and modulus of rigidity. We first calculate Poisson's ratio using the relationship y equal to 3k into 1 minus 2 sigma. We substitute for y as 2 into 10 raised to 11 for Young's modulus 13.3 and then calculate sigma. So before we substitute, we can first write this equation so that sigma is on one side and the rest of the quantity is on the other side and then calculate sigma. So sigma is equal to 1 minus 2 sigma is equal to 1 minus y divided by 3k, and therefore sigma is equal to half minus y divided by 6k. Calculation is simple. 2 into 10 raised to 11 divided by 6 into 13.3 into 10 raised to half minus 1 divided by 3 into 13.3 multiplied by 10. Now it is a simple calculation. This finally gives us the value of sigma 0.25. Sigma is unitless, so no unit. Second problem. A silver wire is 0.032 centimeter in diameter, 2 meter long, vertically hung, and it elongated by 0.1 centimeter when a mass of 0.32 kg is hanged at the lower free end. We have to calculate Young's modulus, and given shear modulus eta, we have to calculate the Poisson's ratio for silver and change in the diameter of the wire. Again, a simple problem. We have to use certain formulas and then substitute the values, calculate the answer. We first write down the data given. We are given diameter. It is 0.032 centimeter. The length of the wire, the original length, is 2 meter. Now here length is in centimeter, the diameter, and here it is 2 meter. So here we have centimeter and here we have meter. So a certain unit must be same in all quantities. So if it is centimeter here, we must bring centimeter here also, or if it is meter, we make centimeter into meter. So we better take centimeter in meter. So how do we convert? We simply multiply it 0.032 by 10 raised to minus 2 and we get the diameter in meter. So now we have diameter and length both in meter. Third information is elongation. Elongation is denoted by small l and it is 0.1 centimeter. We convert it into meter. Again we multiply it by 10 raised to minus 2 and it is in now meter. Fourth information is mass 0.32 kg. It's already in SI unit. We take all the units in SI system. Modulus of rigidity eta is also given. 2.86 into 10 raised to 10 Newton per meter square. We have to find Young's modulus, which is denoted by capital Y, Poisson's ratio, denoted by sigma, and change in diameter. We have a steel wire which is 2 meter in length and its diameter is 0.032 centimeter, and a load of mass 0.32 kg is suspended from the lower free end of the wire, due to which the length of the wire increases by an amount 0.1 centimeter. So this information is sufficient to calculate Young's modulus. We use the definition of Young's modulus to calculate it. Young's modulus is equal to tensile stress, which is the force per unit area, divided by tensile strain, which is the change in length divided by original length. In this formula, there is a force which is not given to us, and A is the area of cross section of the wire, which is also not given. We are given capital L, the original length of the wire, and small l, the change in length of the wire. So using second law of motion, we can write force as mass into acceleration. Mass is given and acceleration is due to gravity, which is known, and we express area in terms of diameter of the circular area of cross section of the wire. So we write y equal to, before we make these substitutions, we write this equation in this way, and then we replace force by mass into acceleration due to gravity divided by area expressed in terms of diameter is pi d square by 4. So we finally have 4 we write this as 4 mgl divided by pi d square. Now all the quantities are given, we just substitute them. Mass is 0.32 kg, acceleration due to gravity g is 9.8, original length is 2 meter, we take pi as 3.14, and diameter is 0.032 into 10 raised to minus 2 meter. Calculation is simple, and we finally get y equal to 7.8 into 10 raised to 10 Newton per meter square. When all the quantities are taken in SI unit, our Young's modulus will also be in SI unit. 7.28 into 10 raised to 10 Newton per meter square. This is the Young's modulus. Now we calculate Poisson's ratio, sigma. We can calculate it from Young's modulus and shear modulus using the relationship y equal to 3k into 1 minus 2 sigma. The same relationship that we used in the previous problem. Again, we can write this equation as sigma equal to half minus y upon 6k. Young's modulus is just calculated, 7.8 into 10 raised to 10, and the shear modulus, It is 2.86 into 10 raised to 10. This is a simple calculation which finally gives us the value of sigma. Zero point 0.365. Now we calculate change in diameter. DD. The change in diameter is governed by Poisson's ratio of the material. So we write the formula for Poisson's ratio, and from the value we have just calculated for the Poisson's ratio, we calculate change in diameter. Poisson's ratio is equal to lateral strain, which is the change in diameter upon original diameter divided by longitudinal strain, which is the change in length divided by original length. So all the values are given. Poisson's ratio is 0.365. Change in diameter is to be found out. Original diameter is 0.032 into 10 raised to minus 2 meter divided by change in length. We missed change in length in the previous calculation for Young's modulus. Here we have a change in length 0.1 into 10 raised to minus 2 meter. And now the answer is 7.8. Change in length is 0.1 into 10 raised to minus 2 meter and divided by original length, which is 2 meter. So we can rearrange all this and get the change in diameter to be 2 into 0.365 multiplied by 0.032 into 10 raised to minus 2. It is 0.1 into 10 raised to minus 2 into 0.365 into 0.032 into 10 raised to minus 2 divided by 2. After calculating, it's DD, the change in diameter on the left hand side. Finally, 5.84 into 10 raised to minus 8 meter. This is the change in diameter. Another interesting problem, we have a block of lead and its original volume is 0.493 centimeter cube. This is the volume. Now this is the volume of the lead under atmospheric pressure. When the same block of lead is taken to the taken into the sea, there is a pressure of water above it and around it onto the lead block. So because of the pressure of water, the volume of the lead block will decrease. So lead block is kept at the base of or at the bottom of sea, and the pressure at the seabed, that is at the bottom of sea, is 8.6 into 10 raised to 89 per centimeter square greater than at the sea surface. So because of this higher pressure, the volume of lead block will decrease, and we have to calculate this decrease in the volume of the lead block or and the new volume of the lead block. So we first write down the data. The original volume V is 0.493. The length is expressed in centimeter everywhere in all the quantities, so we need not convert this into the SI system. So the change in volume or the final volume that we will calculate will also be in the centimeter cube. Second, we are given the pressure increase at the seabed is 8.6 into 10 raised to 8 time per centimeter square. So already there is atmospheric pressure when the block is outside the sea, it is on the ground, and when it is taken to the seabed, the pressure increases by 8.6 into 10 raised to 8 9 per centimeter square. So pressure increase, which is dP, is 8.6 into 10 raised to 8 9 per centimeter square. We note that all the quantities, all the units are in CGS system. So if all the units are in the CGS system, we need not convert to other system of unit. So final value that we calculate will also be in the CGS system of unit. The bulk modulus of the lead block is 4.8 into 10 raised to 11 9 per centimeter square. We can convert all these quantities in SI units, but we really don't require to do that because all of them are already in a CGS system. So we work in the CGS system only, and our final value that we calculate will also be in the CGS system. We have to calculate final volume. So suppose this is the initial volume, we have to calculate final volume. Solution is simple. The problem may look difficult at first, but the solution is very simple. We only have to use the formula for bulk modulus. Bulk modulus is given by volume stress, which is force upon area, divided by volume strain, which is the change in volume divided by original volume. We have to calculate the change in volume. There is a negative sign also because change in volume is negative because the volume decreases, but the volume strain is always positive. So we have to make this quantity positive, and therefore we add negative sign by hand. Force upon area is the pressure. Now there is additional pressure due to seawater on block lid, lid block. So that additional pressure is dP. The force upon area, the additional pressure on a lid block is dP, and we write it like this. So we rewrite it in a simpler form, dP by dV into V. Bulk modulus is given to us. It is 4.8 into 10 raised to 11. So we write 4.8 into 10 raised to 11, and the increase in pressure dP is 8.6 into 10 raised to 8. 8.6 into 10 raised to 8. We have to calculate the change in volume, and the original volume is 0.493. I attach suffix Vi. So we have to find final volume. So instead of, we write this change in volume like this. We write change in volume as is Vi, and Vf minus Vi. Here the original volume is 0.493. 0.493. 0.493 original volume minus 8.6 into 10 raised to 8 divided by Vf minus, here also we write 0.493 for the original volume, 0.493. On the left hand side we have 4.8 into 10 raised to 11. So 4.8 into 10 raised to 11. We take 0.493 on the left hand side, 0.493, and here 8.6 into 10 raised to 8 divided by VA minus 0.493. Then we have VF minus 0.493 equal to minus 8.6 into 10 raised to 8 divided by 4.8 into 10 raised to 11 multiplied by 0.493, and therefore we have VF equal to 0.493 minus 8.6 into 10 raised to 8 divided by 4.8 into 10 raised to 11 to 0.493. Now we only have to do the calculation, and finally we get the final value. It is 0.492 centimeter cube, the final value. Another problem. A copper wire has 1 millimeter diameter and 2 meter length, and mass of 5 kg is hung from the lower free end of copper wire, due to which the copper wire undergo extension. We have to calculate that extension. We are given the Young's modulus of copper. So from Young's modulus we can find out extension produced. We simply use the formula for Young's modulus. Young's modulus, as we have seen in one of the previous problems, that it is given by mgl divided by pi d square by 4. That is, you can write it as mgl pi d square. The mass attached is 5 kg. Acceleration due to gravity is 9.8, and the original length is 2 meter, pi is 3.14, and diameter is 1 millimeter, which we write in meter. 1 into 10 raised to minus 3 meter. Again we miss the change in length L, which is the extension. So this is the extension. Young's modulus is 11 into 10 raised to 10. Therefore, the extension L is equal to 4 into 5 into 9.8 to 2 divided by 3.14 into 10 raised to minus 3 into 11 into 10 raised to 10. On calculating, we get the extension 0.11 into 10 raised to minus 2 meter, which is 0.11 centimeter, the extension. Next, we calculate the minimum diameter of the copper wire so that the elastic limit of the copper wire will not be exceeded. That is, the copper wire will not break. So, the elastic limit of copper is given to us. It can sustain the stress maximum, this stress 1.5 into 10 raised to 9 dyne per centimeter square. If the stress in copper wire exceeds this value, it will break. So this is the maximum stress the copper wire can sustain without breaking. So this limiting value of the stress correspond to a certain minimum value of the diameter, which must not be crossed for the wire not to break. So the elastic limit is given to us. Elastic limit means maximum stress the wire can sustain. The stress is equal to maximum stress. The stress given to us is the maximum stress. Maximum stress is equal to how much is it given? It is 1.5 into 10 raised to 9 here. 1.5 into 10 raised to 9. It's given in dyne per centimeter square. So unit of length is centimeter and the unit of force is dyne. So we need not bother about it. We can calculate the diameter, and the diameter that we will get will be in centimeter. So maximum stress is the force upon area equal to 1.5 into 10 raised to 9. The force on wire correspond to the load of mass of 5 kg. So according to second law of motion, we write force as mg and we write area as pi d square by 4 equal to 1.5 into 10 raised to 9. So mass is 5, acceleration due to gravity is 9.8. We have 4 here which comes from the denominator. Pi is 3.14 and we have to calculate diameter. So this diameter correspond to a minimum value which correspond to the maximum stress given on the right hand side, 1.5 into 10 raised to 9. So the minimum diameter, I write minimum diameter like this. Minimum diameter will be 4 into 5 to 9.8 divided by 3.14 into 1.5 into 10 raised to 9. Therefore, minimum diameter equal the square root of 4 into 5 into 9.8 divided by 3.14 into 1.5 into 10 raised to 9. After calculation, we get minimum diameter 6.4 into 10 raised to minus 2 centimeter. If the diameter of the wire become less than this value, then for a given load of 5 kg, the wire will have a stress greater than the maximum stress it can suffer, the elastic limit, and it will break. Determine the force per unit area required to compress a volume of water by 1%. Bulk modulus is given. Force per unit area means we have to determine stress basically. We simply use the formula for bulk modulus. K is equal to minus dP upon dV into the original volume. We write it as dP into V upon dV. Water is to be compressed by 1%, means change in volume divided by original volume. It must be 1%. That is 1 upon 100, which is equal to 0.01. Therefore, V by dV will be 1 upon 0.01, that is 100. We substitute V upon dV 100 here and we get K equal to minus dP into 100. So bulk modulus is given 2 into 10 raised to 10. It's given in CGS system 2 into 10 raised to 8 equal to minus dP into 100. Therefore, minus dP is equal to 2 into 10 raised to 6, 9 per centimeter square. We see negative sign still there, but already we are given that the change in volume is 1%. So the volume is decreased by 1%. It is given to us already. But dV in our formula does not represent decrease in volume, but actually it is the increase in volume. So here we should write negative sign, because by dV by V we mean increase in the volume, and actually the volume has decreased. So increase in volume will have a negative numerical value. So we write negative sign, and then here also comes negative sign, and then negative negative simply cancels, and we have a positive sign here. So finally we have dP equal 2 into 10 raised to 6 9 per centimeter square. We made one mistake here. It is 10 raised to 10, not yet, and therefore here we will have 8. Is 10, it will be 8 here. Next problem. What torque must be applied to a wire 1 meter long, 10 raised to minus 3 meter in diameter, in order to twist one end of it through 90 degrees, the other end remaining fixed? The rigidity modulus of the wire is given. As we know that when the wire is twisted, its layer undergo displacement, and when the layers of the material undergo displacement, the relevant modulus of elasticity is the modulus of rigidity. This problem is based upon a simple formula which relate all the quantities given in this problem. The formula is the torque is equal to pi n a4 divided by 2L into theta. This eta is modulus of rigidity, A is the radius of the wire, and small l is the length of the wire, theta is the twisting angle producing it. So we write this formula in terms of diameter because we are given diameter. So d upon 2 raised to 4 divided by 2L theta, pi eta d raised to 4 upon 2L into 8, sorry, 16, and then theta. We take pi to be 3.14. The modulus of rigidity is 2.8 into 10 raised to 10, 2.8 into 10 raised to 10. The diameter is 10 raised to minus 3 meter, 10 raised to minus 3. The angle is 90 degree, it means pi by 2 radian. Angle must be taken in radian system, because in our formula we assume radian measure of angle. 2 into the length of the wire, the length of the wire is 1 meter multiplied by 16. The simple calculation gives us the torque required for producing such a twist, and it is 4.318 into 10 raised to 3 Newton meter, the unit of torque. All the quantities are given in SI system, so unit of torque will also be in SI system. A steel wire of diameter 3.6 into 10 raised to minus 4 meter and a length 4 meter. It extends by 1.8 into 10 raised to minus 3 meter under a load of 1 kg. And the twist is also produced of 1.2 radian when it is subjected to a torsional torque of 4 into 10 raised to 5 Newton per Newton meter. Find the values of Y, eta, and sigma, the Young's modulus, shear modulus, and Poisson's ratio. We write data. Diameter is 3.6 into 10 raised to minus 4 meter. Original length is 4 meter. Mass attached is 1 kg. Twisting theta is 1.2 radians. Torsional torque, the torque which causes twist in the wire, it is 4 into 10 raised to 5 Newton meter. We have to calculate Young's modulus, Poisson's ratio, and shear modulus. We can calculate Young's modulus directly from its definition. We are given all the quantities required for calculation of Young's modulus. Young's modulus is equal to mgl divided by pi d square by 4. Then it is 4 into mgl divided by pi d square. Mass is 1 kg. G is 9.8. Capital L, the original length is 4 meter. Pi is 3.14 and diameter is 3.6 into 10 raised to minus 4 meter. On calculation we get 2.139 into 10 raised to 11 Newton per meter square for Young's modulus. Now we calculate shear modulus, eta. To calculate shear modulus, we are given twist produced in the wire and the torque that causes it. We use this formula. Torque is equal to pi eta A4 divided by 2L. Now it is capital L, the original length, to theta. A is the radius of the wire. We are given diameter, so we rewrite it as, we replace radius A by diameter, so it gives us the 2 into 16 L to twisting angle. We have to calculate eta. So we rearrange and get eta equal to T into L into 32 divided by pi e raised to 4 and theta. Torque, the twisting torque is 4 into 10 raised to 5. Then the original length is 4 multiplied by 32 divided by 3.14. Diameter is 3.6 into 10 raised to minus 4. And the twisting produced is 1.2 radian. Angle must be in radian. On calculation, we get shear modulus equal to 0.8083 into 10 raised to 11 Newton per meter square. Now we have values of Young's modulus and shear modulus. And from these two values, we can calculate Poisson's ratio. We use the relationship Young's modulus equal to 2 eta 1 plus sigma. We rearrange this equation and write sigma equal to Young's modulus divided by 2 eta minus 1. Substituting the values of Young's modulus just calculated and also of here modulus divided by 2 into 0.8083 into 10 raised to 11 minus 1. On calculation we get 0.323, the value of Poisson's ratio. It is unitless. We stop here. Thank you.